A star dies, and a single photon begins a voyage across the cosmos. This is the story of Starlight's long goodbye, the untold fate of particles of light traveling for billions of years. By the end, you will understand the universe in a completely new way, seeing time and space through the journey of light itself. We will follow these ancient messengers from their violent birth in stellar furnaces to their mysterious ends, uncovering how they warp, fade, and carry the secrets of reality across the void. What happens when the universe itself stretches a beam of light into oblivion, and why does a photon not experience the eons it travels? This exploration reveals our own fleeting place in a vast, expanding arena. What does it mean that we are built from stardust and see the universe through its ancient light? Deep within a star's core, a chaotic dance of creation unfolds. Atoms are crushed together with unimaginable force, their very identities changing in a flash of energy. This is nuclear fusion, the universe's ultimate power plant. For a single photon born in this inferno, its existence begins not with a gentle glow, but in the heart of a continuous, violent explosion. The light particle you see from a distant star did not simply wink into being at the surface. It was forged in a place of incredible pressure and heat, a place where hydrogen becomes helium, and in that transformation, a tiny packet of pure energy is set free. Yet this is only the first step of an immense struggle. The newly born photon is immediately trapped. It exists inside an unimaginably dense soup of superheated gas, a plasma so thick that the light cannot travel far in any direction. It collides with electrons and atoms, is absorbed and re-emitted over and over again. Its path to freedom is a random, bouncing walk that can last for tens of thousands of years. Think of it like trying to walk straight through a crowded, chaotic party where everyone is constantly bumping into you, pushing you back, and sending you in a new, random direction. The photon fights its way outward, inch by agonizing inch, until it finally reaches the star's surface, the photosphere. Here, the density suddenly drops. There are no more atoms in its way. After its long imprisonment, the photon is finally set free into the open void. In that single, defining moment, its epic journey across the cosmos truly begins, carrying within it the exact story of its violent birth and the unique elemental signature of the star that created it. But freedom from the star's chaotic interior does not mean an easy escape. The photon now faces the immense, invisible grip of the star's gravity. According to Einstein's theory of general relativity, gravity is not just a force, but a warping of the fabric of space and time itself. Even though light has no mass, it must travel along these curves in space-time. So, as our photon pushes away from the stellar surface, it is essentially climbing out of a deep, gravitational well. This climb comes at a cost. The photon must expend energy to escape this powerful pull. We do not see it slow down because light always travels at the same constant speed. Instead, this lost energy reveals itself in a different way. The light wave stretches ever so slightly. Its color shifts toward the red end of the spectrum. This is the phenomenon of gravitational redshift, a subtle but permanent change to the photon's very identity. Imagine rolling a marble up a steep, soft hill. The marble does not slow down, but the effort of climbing makes it lose some of its vibrancy, its intensity. That is what happens to the photon. This initial, subtle reddening is a profound preview. It is the universe's first lesson in how gravity will bend and shape the photon's journey across the cosmos. a faint fingerprint left by its home star as it finally breaks free and enters the vast, empty expanse between the stars. And so the photon escapes its star's gravity, launching into an ocean of perfect black. It moves at the ultimate speed, a constant 300,000 kilometers every single second. This is not a speed we can truly comprehend. It means this particle of light could race around our entire planet 7.5 times in the blink of an eye. Yet here, in the interstellar void, that incredible speed feels almost insignificant. The photon is now on a marathon through a near-perfect vacuum, a realm of such profound emptiness it defies human imagination. For millions of years, it will streak through this darkness. Its path is a perfect, unwavering straight line, a trajectory set the moment it left the star's chaotic surface. What does it encounter on this epic leg of its journey? Almost nothing. It might, once every few centuries, pass near a lonely hydrogen atom or graze a microscopic speck of cosmic dust. These are mere whispers in an endless silence. The sheer scale of this emptiness is the true message. The average distance between stars in our galaxy is so vast that crossing it requires spans of time longer than all of human civilization. This transforms the photon into something more than just a particle of energy. It becomes a flawless time capsule, carrying an unaltered record of its star's composition, temperature, and the very moment of its birth. It is a silent, high-speed messenger from an era long before our sun even ignited, traveling through a void so immense that its journey is one of the most solitary phenomena in the entire universe. But the photon's long journey through the silent void is not the end of its transformation. A far more profound change is happening on the grandest scale imaginable. The very fabric of space through which it travels is not static. It is stretching, expanding like the surface of an inflating balloon. This cosmic expansion does something extraordinary to our photon. As the space between galaxies widens, the light wave traveling through that space is itself stretched. Its wavelength grows longer. This is the phenomenon of cosmological redshift. Think of drawing a wave on a rubber band, then slowly pulling both ends. The crests and troughs of that wave would move farther apart, the pattern elongating. That is the exact fate of our photon over billions of years. A particle of light that was born as a brilliant, energetic blue can be stretched into the low-energy red part of the spectrum. If its journey is long enough, it may be stretched completely beyond what our eyes can see, into the infrared or even into the domain of radio waves. This redshift is not just a color change, it is a direct message from the cosmos written into the light itself. The amount of stretching is a perfect measure of how much the universe has expanded during the photon's travel time. That makes every distant photon we observe both a cosmic ruler, telling us the scale of its journey, and a perfect clock, revealing the immense eons that have passed since it began its voyage. This subtle stretching of starlight is the most fundamental signature of our dynamic, expanding reality. Yet even this near-perfect vacuum between the stars is not the final frontier. When our photon escapes the gravitational pull of its home galaxy, it enters a realm of even greater emptiness, the space between galaxies. Here, it encounters the intergalactic medium. This is not a true void, but a ghostly, superheated fog of ionized gas, a plasma so thin it contains only a few atoms per cubic meter. For a single photon, this is like a lone traveler crossing an entire continent and encountering only a handful of misty droplets along the way. But a journey spanning billions of years changes everything. The cumulative effect of these rare encounters becomes significant. The photon, as it races through this diffuse plasma, can brush against a free floating electron. When this happens, the electron recoils, scattering the light and sending it off on a minutely different path. This is Thomson scattering, a whisper-quiet friction on a cosmic scale. Each individual interaction is vanishingly small, a deflection almost too tiny to measure. Yet over millions of light years, this constant, gentle buffeting acts like a cosmic sandpaper, very slightly blurring the sharp, pristine information the photon carried from its star. It is a gradual, imperceptible dimming and softening of the original signal. The photon is engaged in a subtle battle against the faintest traces of matter, a struggle that slowly erodes its perfect story across eons. This is how the universe itself, through the faintest breath of substance in the deepest voids, leaves its own faint smudge on the light of ancient stars. But the photon's path is never truly straight. As it voyages for eons, it may drift near a colossal island of stars, a galaxy, or an even larger cluster of galaxies. These are not just collections of suns, they are the universe's heaviest anchors, and their immense mass warps the very fabric of space and time around them. Our photon, traveling along what it believes is a direct route, suddenly finds its trajectory curving. It is not being pulled by a force, but simply following the shortest path through a cosmos that has been bent out of shape. This phenomenon is gravitational lensing, a cosmic detour written into the geometry of reality. From our perspective, the effect is like looking through a giant, rippled lens. The light from a distant galaxy can be stretched into a faint, luminous arc, or a single quasar can appear as multiple, identical images scattered around a foreground galaxy. For the photon itself, this is a forced rerouting, a bend in the road it cannot avoid. This silent, invisible guidance system does more than just alter paths. It can also act as a natural telescope, concentrating the light and magnifying the appearance of incredibly distant objects that would otherwise be far too faint for us to see. Most profoundly, the amount of bending we observe often reveals far more mass than we can see with our telescopes. This is the ghostly signature of dark matter, the invisible scaffolding of the cosmos, revealed only by the way it steers the ancient light on its long journey home. Yet for the photon itself, this epic voyage spanning billions of years never happens. The moment it bursts free from its star and the moment it is finally absorbed, perhaps by the lens of a telescope or the retina of your eye, are one and the same instant. This is the most profound paradox of its existence, a direct consequence of traveling at the absolute speed limit of the cosmos. According to Einstein's theory of special relativity, as an object approaches the speed of light, time for that object slows down relative to the rest of the universe. For the photon, which lives its entire life at that ultimate speed, time does not merely slow, it stops completely. Its internal clock never ticks. It does not experience the emptiness of the void, the gentle pull of gravity, or the slow stretching of its own wavelength. From its own perspective, its emission and absorption are a single, simultaneous event. Imagine if your entire life, from birth to your final breath, was compressed into a single, unblinking flash of awareness. You would not feel the passage of days or years, only the stark reality of beginning and end fused into one. This is the reality for every particle of light. Its multi-billion-year journey across galaxies is a timeless now. This bizarre fact challenges everything we think we know about cause and effect, about the flow of time itself. It suggests that for the universe's most fundamental messengers, the past and future are not separate, but inextricably linked. We, anchored in our slower reality, watch the light's long goodbye unfold over eons, but for the photon, there is no goodbye at all. It is both a newborn and an ancient relic in the very same instant, a silent testament to the strange and beautiful fabric of a reality where time is not absolute, but a matter of perspective. But not every photon we see began its life inside a star. The very oldest light in the universe predates every sun and every galaxy. This is the cosmic microwave background radiation, a faint, cold glow that fills every corner of the sky. Its discovery was a complete accident, a persistent, unexplained static picked up by radio antennas in the 1960s. Astronomers eventually realized this was not a technical fault, but the faint, cosmic echo of creation itself, the afterglow of the Big Bang. These photons have been on an uninterrupted journey for over 13 billion years. They are the ultimate ancient messengers, and they carry a picture of the universe when it was a mere infant, just 380,000 years old. At that moment, the entire cosmos was not a collection of stars and galaxies, but a searing, opaque fog of plasma, a hot, dense soup of particles and light. Photons could not travel freely, constantly bouncing off a thick sea of electrons. Then, in a pivotal cosmic moment, the universe expanded and cooled just enough for atoms to form. The electrons were suddenly captured and the fog lifted. For the very first time, light was set free. The moment of that release is what we see in the cosmic microwave background. It is a baby picture of the cosmos, a snapshot of its fiery beginnings. The subtle patterns imprinted in this ancient light, tiny variations in temperature, are the blueprints for everything that would follow, the seeds from which all galaxies, stars, and planets would eventually grow. These are the most profound long-distance travelers, and their silent, omnipresent whisper is the most direct evidence we have that our universe had a definite, hot, and dramatic beginning. So while a precious few photons complete their epic journeys by landing in our telescopes, this is a vanishingly rare outcome. For every one that we successfully capture, countless trillions more meet a different, far quieter end. Their fate is to become eternal wanderers in a cosmos growing ever colder and more diffuse. As the universe expands relentlessly, these photons see their wavelengths stretched not just for billions of years, but for trillions and then forever. Their energy, once vibrant and specific, steadily diminishes, fading towards an infinitesimal whisper. A brilliant blue photon from a young galaxy will eventually be stretched far beyond the red, into the microwave, then the radio, and finally into wavelengths so long they are practically immeasurable. These particles of light do not die, but they effectively vanish from the observable story of the cosmos, becoming one with a cold, faint background sea of radiation. This is the ultimate legacy of all the stars that ever were, a ghostly echo of their combined light slowly dissolving into the expanding dark. There is another, equally solitary conclusion. A photon might, after billions of years of flawless travel, chance upon a random, cold speck of interstellar dust floating in the void of a distant galaxy. In that final, unobserved moment, it is absorbed. Its immense journey, a story written across cosmic time, concludes not with a discovery, but with the most mundane of transformations. Its energy is converted into a minuscule, undetectable amount of heat, warming a single dust grain by a fraction of a degree. No one sees it, no instrument records it. Its entire history, from stellar forge to silent dissolution, is known only to the universe itself. This is the most probable destiny for Starlight, a long goodbye that ends not with a bang, but with the quietest of sighs, a return to the cosmic background from which all structure first emerged. Yet for one photon in countless trillions, the long silence is finally broken. Its path, set in motion billions of years ago, by pure chance intersects a small, cold circle of glass and metal orbiting a pale blue dot. This is a cosmic lottery of unimaginable odds, a trajectory so perfectly aligned that after eons of empty travel, the photon does not miss its target by a millimeter. It strikes the polished mirror of a great telescope like Hubble or James Webb. In that final, definitive instant, its epic journey ceases. The photon is absorbed, and its ancient energy is transformed into a tiny, measurable electrical current. This signal is a whisper from the deep past. It is one pixel of light, one point of data in a vast digital image. We collect millions of these individual whispers, each from a different photon that won the same incredible lottery. Slowly, painstakingly, we assemble them. A faint, fuzzy smudge resolves into a spiral galaxy. The subtle red shift of its collective light tells us the immense distance it has traveled. We are not just looking at a picture of a distant galaxy. We are witnessing the final, simultaneous moments of countless ancient voyages, each culminating in a flash of data on a screen. That beautiful image of a swirling island of stars is, in truth, a mosaic of endings. It is a portrait painted by the last breaths of light from a galaxy that may have itself faded eons ago. We see its ghost assembled one lucky photon at a time. Each photon that ends its journey in our telescope is far more than a point of light. It is a perfect, self-contained data packet from the deep past, carrying a wealth of specific information locked within its properties. The most fundamental clue is its energy, which we perceive as its color. A high-energy blue photon tells a story of a ferociously hot, young, massive star. A lower-energy, redder photon whispers of a cooler, older stellar giant. By analyzing the precise mix of colors in the starlight from a distant sun, we can decode the exact chemical composition of that star, identifying the unique spectral fingerprints of hydrogen, helium, carbon, and oxygen present in its outer layers. The light is a direct chemical assay from billions of light years away, but the information does not stop there. The photon's polarization, the specific orientation of its vibrating electric field, acts as a cosmic compass. As light travels through the vast magnetic fields that thread the spaces between stars, its polarization can twist and align. By measuring this subtle shift, we can map these invisible magnetic structures, tracing the ghostly architecture of the galaxy itself. Even the precise timing of a photon's arrival holds a secret. When a ripple in space-time, a gravitational wave, passes through the cosmos, it minutely stretches and squeezes the distances between objects. This can affect the travel time of light. By monitoring the incredibly regular pulses of light from distant neutron stars called pulsars, and noting tiny, synchronized delays in the arrival times of their photons, we can detect the passage of these cosmic waves, listening to the echoes of colliding black holes. We are essentially using light itself as the most precise ruler ever conceived. Alone, a single photon is a single letter, a lone data point. But by collecting millions of them, we slowly assemble words, then paragraphs, and finally entire chapters of a cosmic history book. Our telescopes are not merely cameras, they are time machines and decryption devices, patiently unraveling the stories carried by these ultimate messengers, stories that began their telling before our world was even born. That final, definitive moment of absorption marks the true end of the line. After crossing billions of years of expanding space, a photon's journey concludes in a sudden, intimate encounter with an atom. It does not bounce off or slow down, it is simply gone, vanishing as an independent entity. The atom, typically within a molecule in the retina of your eye or the silicon of a camera sensor, acts as the final destination. It absorbs the photon's entire quantum of energy in one instantaneous gulp. This energy transfer does something remarkable to the atom. It excites one of its electrons, boosting that tiny particle to a higher, unstable energy level. Think of it like a marble being instantly teleported to a higher step on a staircase, a step where it cannot comfortably remain. This newly acquired energy cannot just disappear, it must go somewhere. The fate of that energy, the final legacy of the photon, now depends entirely on its surroundings. In the specialized cells of your retina, this energy triggers a complex chemical cascade, an electrochemical signal that races along your optic nerve to your brain, where it is interpreted as a point of light, a single star in your perceived sky. In a telescope's digital sensor, the energy creates a tiny electrical charge, a single data point in a vast image. But this re-emission is a special case, a useful conclusion for us as observers. Far more often, the absorbed energy is not re-radiated as new light. Instead, it is converted directly into random motion, into heat. The energy of a photon that traveled from a distant quasar can end its existence by warming a single dust grain in deep space by a minuscule, unobservable fraction of a degree. Its epic story, written across cosmic time, dissolves into the bland background of thermal energy. This is the photon's ultimate transformation, a final surrender of its unique identity. It ceases to be a messenger from a specific star and becomes one with the general hum of the universe, its journey complete, its long goodbye finally whispered into silence. This dual nature is not a quirk of our experiments, but the core reality of light's existence across the cosmos. From the moment it leaves its star, a photon is both a localized particle, a tiny bullet of energy, and a spread-out wave of probability. This wave is not a physical ripple like water, but a map of likelihood, a description of where the particle is most probably found. On its billion-year journey, the photon's wave function does not follow a single, razor-straight line. It effectively explores every conceivable path between its origin and its destination, a ghostly fan of potential routes spreading through the universe. It samples trajectories that bend slightly around invisible gravitational wells and paths that take detours through entirely empty voids. All of these possibilities exist simultaneously until the very last moment. This is not a metaphor, it is the mathematical reality of its voyage. The final act, the moment the photon is absorbed by your eye or a telescope, is what forces this spread-out wave to collapse. All those ghostly possibilities instantly vanish, and the photon manifests as a particle in one specific location, as if it had traveled a single, definite path the entire time. We can never know which precise route it took through the gravitational fields and dust clouds of the intergalactic medium. That fundamental uncertainty is woven into the fabric of space-time itself. The universe, at its most basic level, operates not on certainty but on probability, and the light from distant stars is a constant, flowing reminder of this beautiful, underlying weirdness. This silent force, dark energy, is the unseen hand reshaping the cosmos. It is the reason the very vacuum of space is not empty, but possesses a strange, repulsive gravity that pushes galaxies apart at an ever-increasing rate. For our photon, dark energy is not a character in its story, but the relentless director of the entire play. It is the ultimate cause of the cosmological redshift, the reason the photon's wavelength stretches over billions of years, slowly draining its vitality and shifting its color. Without this mysterious influence, the universe's expansion would be gradually slowing down due to the collective pull of all matter. Instead, dark energy dominates, ensuring that every new volume of space that forms carries with it more of this repulsive force, accelerating the whole process. This means the fate of future Starlight is one of increasing solitude. A photon emitted from a galaxy a billion years from now will find itself in a universe expanding far more rapidly than the one we observe today. The space it must cross will be stretching at a faster and faster pace, stretching its wavelength more severely and over a greater total distance. Its journey will be longer, and by the time it might arrive at some distant observer, its signal will be exponentially weaker, its energy faded into a faint whisper. Dark energy is thus writing the final, quiet chapters for all starlight. It is ensuring that the most distant galaxies we can see today will one day be pushed beyond a cosmic horizon, their light stretched into complete invisibility and their stories lost to the void. The long goodbye of starlight is not a temporary phase, but the permanent, accelerating condition of our cosmos, orchestrated by this most profound and elusive mystery. The frozen clock of the photon is only half the story of time's strange behavior. From our vantage point on Earth, we watch the universe in motion, and that motion directly warps the timeline of the light we receive. Imagine a distant galaxy hurtling away from us at a significant fraction of light speed. The very fabric of its motion stretches time itself. The processes we observe there, from the flicker of individual stars to the steady pulse of a quasar, appear to unfold in slow motion compared to our own clocks. This is the phenomenon of time dilation, a core prediction of Einstein's special relativity. We are not just seeing the galaxy as it was billions of years ago, we are seeing it play out in a kind of cosmic slow motion, its internal clock seemingly ticking far more slowly than our own. This temporal distortion is imprinted directly onto the stream of photons arriving at our telescopes. The rate at which these individual particles of light reach us is altered, providing a direct measurement of the source's velocity through the expanding cosmos. But motion is not the only force that bends time. Gravity, the warping of spacetime by mass, creates an even more profound effect. A photon climbing out of the immense gravitational well of a dense galaxy cluster or a supermassive black hole does not just lose energy and redshift, it also experiences a dramatic slowing of time from our perspective. The light from a star orbiting close to such a monster appears to us to be emitted at a glacial pace, its intrinsic variations stretched out over a longer duration. This gravitational time dilation means the light we collect acts as a direct probe, carrying within its arrival rate a hidden diary of the intense gravitational fields it has traversed. By analyzing these subtle shifts in timing, we can weigh the invisible monsters lurking in galactic cores and map the distribution of dark matter halos. The photon, timeless itself, becomes the ultimate messenger of time's malleability, a silent witness to the fact that the universe has no single, universal clock, but a tapestry of timelines, all woven together by the twin threads of motion and gravity. These ancient photons do more than just tell their own stories. They form the very foundation of how we measure the cosmos. Astronomers have built a cosmic distance ladder, a step-by-step method to gauge the vast scales of the universe, and every rung of this ladder is constructed from the properties of light itself. The process begins close to home, using simple geometry to measure the distances to nearby stars with a technique called parallax. But to reach beyond our own galactic neighborhood, we need something more powerful, a set of cosmic landmarks with a known, predictable brightness. These are the universe's standard candles, celestial objects whose intrinsic luminosity is understood. The most famous of these are Cepheid variable stars, pulsating giants whose rate of pulsation is directly tied to their true brightness. By observing a Cepheid and measuring its pulsation period, we know exactly how bright it truly is. We then compare this known, intrinsic brightness to how dim it appears from our vantage point. The difference, the dimming, is a direct gauge of distance because light fades in a precise and predictable way as it travels across space. Each photon we collect from that Cepheid is a tiny measurement of that fading, a single vote confirming the immense void it had to cross. But Cepheids only take us so far. To climb higher on the distance ladder and probe the deepest reaches of space, we need an even brighter beacon. This is where Type Ia supernova come in. These titanic stellar explosions occur in binary star systems and have a very specific, repeatable mechanism, which means they always reach nearly the same peak brightness. When one of these supernovae erupts in a distant galaxy, it can outshine its entire host, becoming a brilliant, temporary standard candle visible across billions of light years. We measure the redshift of its light, which tells us how much the universe has stretched during its journey, and we measure its apparent dimness. By combining these two pieces of data, the redshift and the dimming, we can calculate not just the distance to the supernova, but also the rate of the universe's expansion throughout cosmic history. Every single photon from that dying star is a crucial data point in this calculation. Alone, it is a faint whisper, but together, millions of them paint a three-dimensional map of the observable universe, revealing the large-scale structure of galactic filaments and vast voids. This entire edifice of cosmic cartography, our understanding of where everything is and how it is moving, rests entirely on the reliable, measurable journey of light from these stellar messengers. This simple fact transforms the night sky into a grand historical archive. Every point of light you see is a messenger from a different era. The glow of the Andromeda Galaxy, our nearest large neighbor, is 2.5 million years old by the time it reaches your eyes. You are witnessing it as it was before humans ever walked the Earth. Push your gaze further to the vibrant pinwheels and fuzzy ellipticals captured by great telescopes, and you are looking billions of years into the past. A photon from a galaxy 1 billion light-years away does not just tell a story of distance, it is a literal fossil, a 1 billion-year-old snapshot of that island universe. Our most powerful observatories are, in their truest function, time machines. They do not show us the universe as it is, but as it was, a layered tapestry of cosmic history. The deeper we look, the further back we travel. The faintest, most redshifted smudges of light at the edge of our observational horizon are portraits of the universe in its raw, formative youth, a time when the first galaxies were just assembling themselves from the primordial dark. We are not passive observers of a static cosmos. We are archaeologists of time itself, sifting through layers of ancient light. Each photon that lands on a sensor is a piece of evidence, a single frame in a movie that spans billions of years. By collecting these frames from different distances, we can actually watch the universe evolve. We see that young galaxies were more chaotic, more prone to violent collisions and bursts of star formation, while older galaxies have settled into quieter, more orderly shapes. The light we gather is the ultimate cold case file, allowing us to reconstruct the life story of the cosmos, from its fiery beginnings to the structured universe we see around us today. Every star you wish upon is an echo, and every galaxy a ghost, reminding us that the sky is not a ceiling, but a window into the profound and ever-unfolding past. But this seemingly eternal existence raises a profound and unsettling question. Can light itself die? The conventional answer has always been no. A photon, born massless and traveling at the ultimate speed, should be the universe's perfect immortal traveler, its energy preserved forever. Yet physics at the very edge of our understanding whispers a different, more haunting possibility. Some theories suggest that if a photon possessed even an unimaginably tiny rest mass, a billionth of a billionth of a billionth the mass of an electron, its immortality would be an illusion. Over timescales that dwarf the current age of the universe, trillions upon trillions of years, such a photon could spontaneously decay. It would vanish, transforming into a pair of the lightest particles we know, perhaps a neutrino and an antineutrino. This would not be a dramatic explosion, but the quietest of disappearances, a single point of starlight winking out in the endless dark. The universe would not fade with a bang, but with a slow, inexorable dimming. The collective glow of all the galaxies would very gradually soften, like a cosmic light on the faintest of dimmer switches, ebbing away over eons too vast to comprehend. We have absolutely no evidence that this is happening. Every observation we have confirms the photon's stability, but the mere theoretical possibility forces us to confront the ultimate fragility of the cosmos. It suggests that even the most fundamental constants, the rules we take for granted, might only be temporary. The oldest photons, those from the cosmic microwave background that have journeyed for over 13 billion years, would be the first candidates for this decay. Their immense age makes them the most likely, if any decay occurs at all, to simply cease their voyage. This transforms them from eternal messengers into potential ephemeral whispers, their long good by carrying a final, absolute silence. If true, it would mean the universe's memory, written in light, is not permanent. The stories carried by photons would have an expiration date, and the night sky, however timeless it appears to us, is ultimately on borrowed time. This leads us to a paradox that strikes at the very core of physics. When a photon is absorbed by an atom and its energy is converted into heat or a neural signal, what happens to the story it carried? The atom now holds that energy, but the photon's unique identity, its specific quantum state, its entire history of where it has been and what it has passed through, seems to vanish without a trace. According to the fundamental laws of quantum mechanics, this should be impossible. Information, in the physicist's sense, cannot be created or destroyed. It can be transformed, scrambled, and hidden, but it must be preserved. This principle is known as unitarity, and it is as foundational as the conservation of energy. So when a photon disappears, its information cannot simply be erased from the universe. The apparent loss creates a profound puzzle, one that echoes the infamous black hole information paradox. A black hole, according to classical physics, swallows matter and light completely, seemingly destroying all information about what fell in. Yet quantum mechanics insists this information must still exist somehow. The absorption of a photon is a microscopic version of this same cosmic conundrum. The resolution may lie in the nature of the absorption event itself. The photon's specific quantum state, its polarization, its energy, its phase, does not just vanish. It is transferred into the complex, jostling state of the atom that absorbed it and the surrounding environment. The pristine, ordered information of the photon's journey becomes scrambled, mixed inextricably with the trillions of other quantum states in the atoms around it. It is like a single drop of ink falling into a swimming pool. The ink is not gone. Its molecules are still there, but they are dispersed so thoroughly and chaotically throughout the entire pool that retrieving the original, solitary drop is practically impossible. The information is preserved, but in a form so complex and delocalized that it is forever lost to any practical observation. For the photon, this means its long goodbye is not an erasure, but a transformation into a ghostly, universal whisper, its story woven into the impossibly complicated quantum tapestry of the cosmos, never to be read again, but forever a part of the whole. This accelerating expansion carves a final horizon into the future of the cosmos. The very space between galaxy clusters is not just growing, it is stretching at a rate that will soon become insurmountable for light itself. Galaxies beyond our own local gravitationally bound group are caught in this cosmic current, their recessional velocity increasing with every moment. There will come a time, billions of years from now, when the distance between us and these distant islands increases faster than light can travel across it. It is not that the galaxies are moving through space faster than light, which is forbidden, but that the new space being created between us and them is accumulating at a superluminal rate. When this threshold is crossed, the connection is irrevocably severed. A photon emitted from one of those galaxies at that very moment, aimed directly at us, would find itself in a futile race. It would be like a swimmer trying to cross a river that is widening faster than they can swim, destined never to reach the other side. The light from those stars, their ancient stories and cosmic data, will simply never arrive. The river of space itself will have become too wide to cross. From that moment on, their long goodbye becomes a permanent, silent farewell. The universe, from our perspective, will begin to shrink. The number of new photons arriving from the deep cosmos will not just slow to a trickle, it will stop entirely. The great tapestry of the night sky, woven from the light of countless galaxies, will begin to unravel. One by one, over billions of years, those faint, fuzzy smudges will redden, dim, and then wink out of visibility forever. They will not explode or vanish. They will simply be carried by the expansion of space beyond our event horizon, receding into a darkness from which no information can ever return. For any future civilization that might arise on Earth or within our local group of galaxies, the universe will become a profoundly isolated place. Their night sky will be beautiful, dominated by the merged glow of the Milky Way and Andromeda galaxies, but it will be a lonely beauty. They will have no way of knowing that a vast, populated cosmos of other galaxies ever existed. All evidence of the Big Bang, the cosmic microwave background, and the large-scale structure of the universe will have been pushed beyond their perceptual reach. The cosmos will appear static, small, and eternal, with no clues to its violent, expansive beginning. The great cosmic archive will have closed its most distant wings, its most ancient volumes forever locked away. The long goodbye of Starlight thus culminates in the deepest silence imaginable, a future where the universe's greatest stories are no longer being told because there is no one left to hear them. So we are not just passive collectors of ancient whispers, we are also active listeners for a voice. Hidden within the endless sea of natural starlight could be a single photon with a story unlike any other, a story of design. This is the search for technosignatures, the hunt for light that bears the imprint of an intelligent mind. These are not the random emissions of a stellar furnace, but photons engineered with a purpose. They could arrive as a powerful, tightly focused laser pulse, a brilliant flash so narrow and intense that no natural process could create it. Or we might detect a pattern, a subtle but precise modulation in a star's light, like a series of pulses forming a mathematical sequence or a prime number count embedded in the beam. Even the color could be a clue, an emission concentrated in a part of the electromagnetic spectrum that is unnaturally quiet, a channel chosen for its clarity over the cosmic background noise. To find such a photon would be to fundamentally rewrite its biography. Its multi-billion-year journey would no longer be a tale of random cosmic forces and silent expansion. It would become a narrative of intent. The moment of its creation would not be a chaotic fusion event, but a deliberate act of transmission. Its trajectory would not be a simple escape from a star's gravity, but a carefully aimed message in a bottle, cast into the ocean of space with the hope of finding a shore. The fate of that one particle of light, should we ever capture it, would be staggering. It would cease to be just a data point in an astrophysical survey. It would transform into a cosmic courier, its sole purpose to deliver the most profound news in human history. That single, ancient photon, arriving at our telescope after eons of travel, would carry the confirmation that we are not the only ones who look up at the stars and wonder. Its long goodbye from its source would be, for us, the very first hello. This final moment of absorption is where the cosmos becomes conscious of itself. The photon's entire history, from its violent birth to its silent journey through expanding space, culminates in a single, transformative event, an act of observation. Without this, the voyage is just a potentiality, a story written but never read. When a photon strikes the retina in your eye, it does more than just trigger a chemical signal. It bridges an impossible gap, connecting the macroscopic realm of galaxies and billions of years to the microscopic, private world of your own awareness. You are not a passive screen upon which the universe projects its light. You are an integral part of the circuit, the final component that completes a circuit of causality stretching back to the dawn of time. That spark of perception, the moment you become aware of a star's glimmer, is the universe awakening to one of its own most ancient creations. We often think of ourselves as separate from the cosmos, tiny specks looking out at an immense, uncaring void. But the journey of light reveals a profound and beautiful entanglement. Your act of seeing gives purpose to the photon's eons of travel. You are the destination. This transforms our understanding of our place in the grand scheme. We are not merely inhabitants of the universe, we are its organs of perception. Through our eyes and our instruments, the cosmos achieves a form of self-awareness, capable of reflecting on its own origin, its own structure, and its own breathtaking beauty. The long goodbye of Starlight is, in its final moment, a hello, a meeting between the ancient and the present, between the immense and the intimate. It is a reminder that we are woven into the fabric of reality, not as outsiders, but as essential participants in an unfolding story billions of years in the making. This stream of ancient light is a finite inheritance. Every photon we capture from the edge of the observable universe is a piece of cosmic history that can never be replaced. The galaxies we see today are not permanent fixtures in our sky. The relentless expansion of space, driven by dark energy, is constantly pushing the most distant islands of stars beyond a final horizon. There will come a time for each of them when the space between us stretches faster than light can cross it. When that threshold is passed, the connection is severed forever. The light from those galaxies, their unique stories and elemental compositions, will simply cease to arrive. Their long goodbye becomes an eternal silence. This means the data we are gathering right now is irreplaceable. It is a non-renewable resource, a library whose most distant wings are slowly, inexorably closing to us. This reality imposes a profound ethical duty upon us, the temporary observers. We have a responsibility to observe, to preserve, and to understand this data. It is not merely a scientific pursuit, it is an act of cosmic conservation. We must build the telescopes and the instruments to catch these fading whispers. We must develop the archives and the technologies to safeguard the information they carry for generations yet to come. We are, in a very literal sense, the universe's way of knowing itself. These photons are its memory, its autobiography written in light and radiation. Our failure to listen, to record, and to protect this knowledge would be a permanent loss, not just for humanity, but for the cosmos itself. It would be a story forgotten, a chapter of existence erased before it was ever fully read. Protecting our ability to receive this light, to maintain our window to the deep cosmos, is therefore a duty to history on the grandest possible scale. We are the guardians of a narrative billions of years in the making, and the final recipients of a legacy of light that is slowly but surely fading into the dark. A single photon's voyage is the universe's ultimate synthesis. This journey weaves together every major law of physics into one seamless narrative. Its birth in the stellar core is a quantum event, a flash of energy emerging from the probabilistic dance of particles. That tiny packet of light then travels through a cosmos governed by Einstein's general relativity, its path curved by the gravity of galaxies and its very essence stretched by expanding space. Along the way, its rare encounters with particles of dust or wisps of plasma are stories of thermodynamics, tiny exchanges of energy that slowly, imperceptibly, nudge the universe toward a colder, more disordered state. And its grand fate, whether to be captured or lost forever, is a question of cosmology dictated by the dark energy accelerating the cosmic expansion. This single thread of light connects the impossibly small to the unimaginably large. It links the quantum fire of a single atom's fusion to the vast architecture of galactic superclusters. But the synthesis does not end with physics alone. The story finds its final, most mysterious chapter in the act of observation itself. When that photon is finally seen, when its journey is completed in an eye or a telescope, the chain of physical cause and effect intersects with the emergence of consciousness and knowledge. The universe, through us, becomes aware of its own structure and history. To trace the fate of a photon is therefore to undertake a grand tour of reality itself. It is to see how the rules that govern the tiniest particles are inextricably linked to the evolution of the entire cosmos, and how that cosmic evolution ultimately gives rise to minds capable of understanding it. This is not just one story among many, it is the foundational story, a single strand of light tying together the quantum, the cosmic, and the conscious into one breathtaking whole. The journey of a single photon stands as one of the universe's most epic narratives, a voyage that encapsulates the entire drama of cosmic existence. From its violent birth in a stellar forge to its final moment of perception in an eye or a telescope, this particle of light weaves together the fundamental laws of physics, the architecture of spacetime, and the emergence of consciousness itself. It teaches us that time is not a universal river but a personal experience, that space is not a static stage but a dynamic, stretching fabric, and that our own fleeting lives are intimately connected to events that unfolded billions of years ago. We are not just observers of this cosmic story, we are participants, the final destination that gives meaning to the light's immense journey. The next time you look up at the night sky, remember that you are not simply seeing a static tapestry of distant suns. You are witnessing a river of ancient travelers, each point of light a stream of photons that began its story before our planet even coalesced from cosmic dust. Their long goodbye, spanning eons of empty space and silent expansion, is in its final moment a continuous hello from the deep past, an invitation to learn, to wonder, and to explore the grandest questions of our existence. Let this knowledge inspire you to look deeper and to question further, to see the night sky not as a ceiling, but as a window into a story still being written. We would love to hear your own thoughts on this cosmic mystery in the comments below.